10 gemstones used in modern technology. For centuries, gemstones have dazzled us with their beauty, adorning crowns, rings, and temples. But beyond their brilliance and symbolism, many of these minerals possess extraordinary physical and chemical properties that make them indispensable to modern science and technology. This article looks at 10 gemstones that have moved beyond luxury into laboratories, battlefields, circuit boards, and even outer space. These aren't just pretty rocks, they're future materials. Remember to press and hold the like button, leave a comment, and hit subscribe before we begin. Ranked 10th, Peridot, from volcanic depths to infrared innovation. Peridot isn't just a gemstone, it's a material forged in the Earth's mantle and reborn through the lens of modern technology. Crystallizing deep beneath the surface, often over 90 miles down, this vivid green member of the olivine family surfaces only through potent volcanic activity, or, in rare cases, arrives aboard meteorites. Its composition is unique in that its color is not caused by trace impurities like most gemstones, but by the iron within its crystal structure, giving it a rich glow that ranges from bright chartreuse to deep olive green. But Peridot's story goes far beyond beauty. Peridot is drawing attention in modern material science for its thermal stability, durability under pressure, and optical transparency in the near-infrared range. Researchers have begun to explore its potential in infrared optical systems, high-temperature sensors, and even as a host material in advanced photonic devices. With a Mohs hardness of 6.5 to 7, it's not the toughest gem, but it balances just enough durability with critical optical performance to make it interesting for niche tech applications. Environmentally, Peridot is a standout. Many of its deposits are alluvial, meaning they require far less invasive mining compared to harder-to-reach gems. That makes it a compelling choice in discussions of sustainable sourcing for optically active materials. Peridot carries both a geological legacy and a scientific future. It's a rare combination of natural wonder and material potential, a gemstone with one foot in ancient magma and another stepping into the future of optics. Ranked 9th, Emerald, where ancient beauty meets modern precision. Emerald has long been revered as a symbol of luxury, wisdom, and emotional depth. But in today's world, it's also gaining traction in advanced optical science. As a chromium-rich variety of beryl, emerald owes its vivid green hue to trace elements that give it beauty and unique optical transmission properties, particularly in the visible to near-infrared range. While prized for centuries in crowns and amulets, this ancient gem is now in the lab. With a Mohs hardness of 7.5 to 8, emerald is durable but brittle, limiting it somewhat in mechanical applications. However, its internal structure allows for selective light absorption and filtering, making it a candidate for optical windows, color-specific lenses, and even specialized filters in laser and spectroscopy technologies. Researchers are also investigating emerald's potential in solid-state photonic devices, where materials must endure heat, resist chemical interference, and maintain precise light performance. Emerald's balance of natural imperfection and optical response makes it particularly interesting. Its famous Jardin inclusions, long celebrated by gemologists for their character, can, in some cases, be studied for microscopic internal lattice behavior, offering insight into crystal stress mapping and light scattering models. Emerald's appeal lies in its duality, a natural work of art with untapped material potential. Sourced from places like Colombia, they may also be calibrated components in optical systems, bridging the emotional legacy of ancient royalty with the precision needs of future technology. Ranked 8th, Topaz, where optics and engineering converge. Though often admired for its beauty, Topaz is emerging as a material of increasing value in modern science and technology. As a fluorosilicate mineral with a Mohs hardness of 8, it's one of the hardest silicate crystals, offering exceptional durability, clarity, and thermal stability. These properties make it ideal for scientific instrumentation, particularly in high-pressure environments, laser optics, and light polarization systems. Topaz is notably transparent across the visible and near-infrared spectrum and has low birefringence, qualities that make it useful as a window material in optical instruments. Its predictable cleavage pattern also provides value in materials research, where controlled fracturing under stress is studied. Additionally, Topaz is being explored for thermoluminescent detectors, with applications in medical radiation monitoring and nuclear science. In these applications, it can store and release energy in response to ionizing radiation. Treated varieties such as London Blue Topaz are even being evaluated for use in optical coatings and engineered surfaces. While it may not be as famous as diamonds or sapphires in scientific circles, Topaz quietly delivers a rare combination of optical performance, structural resilience, and material versatility, proving that its value extends far beyond the world of jewelry. Ranked 7th, Zircon, the gemstone that measures time and shapes science. Zircon may sparkle like a diamond, but its true brilliance lies in its ability to record the history of Earth itself. Zircon has become an essential tool in modern geology and material science as one of the oldest minerals ever discovered, with crystals dated at 4.4 billion years old. Its crystal lattice naturally captures trace elements like uranium and thorium, which slowly decay over time, allowing scientists to use zircon for radiometric dating and reconstruct the timeline of planetary evolution. But zircon's contribution doesn't stop at the past. It's increasingly being studied for technological applications due to its thermal stability, high refractive index up to 2.02, and optical transparency across a broad light spectrum from UV to infrared. These properties make zircon viable for infrared optics, high-performance ceramics, and thermal barrier coatings in aerospace and industrial systems. Synthetic zircon-based materials, such as zirconia and zirconium silicate, are widely used in fuel cells, dental implants, and ceramic capacitors, demonstrating that the family of zircon minerals is deeply woven into the world of advanced engineering. Even in gemstone form, zircon's birefringence and optical density make it valuable for high-precision optical calibration, where light behavior must be carefully mapped and manipulated. Zircon isn't just a relic of Earth's origin, it's a functional material with future-facing potential. It bridges the worlds of deep time and deep tech, telling a story that spans primordial magma to photonic systems. Ranked 6th, Spinel, from crown jewels to transparent armor. Spinel has quietly transformed from a historical understudy to a modern material star. Once mistaken for ruby and adorning royal crowns for centuries, Spinel has proven to be more than just visually captivating. With a chemical composition of magnesium aluminum oxide, a Mohs hardness of 7.5 to 8, and a stable cubic crystal structure, Spinel offers a rare combination of optical clarity, toughness, and thermal resistance. These properties have made synthetic spinel a material of choice in various advanced applications. In defense, it's used in transparent armor for military vehicles and protective visors, offering superior strength and clarity across the visible and infrared spectrum while remaining lighter and more durable than traditional glass. In aerospace and optics, Spinel is used in infrared domes, high-speed sensor windows, and laser protection systems where resistance to pressure, heat, and impact is critical. Its optical isotropy and resistance to scratching make it ideal for precision lenses and smart wearable devices, including head-up displays and thermal imaging systems. What sets Spinel apart is how it looks and performs under extreme conditions, balancing aesthetics with advanced material performance. Spinel is no longer the hidden gem, it's the engineered crystal behind some of the world's most advanced protective and optical systems, proving that brilliance isn't always about shine, but strength with vision. Ranked 5th, Garnet, the gem powering lasers, lenses, and beyond. Garnet is more than a birthstone. It's a foundational material powering some of the most important advancements in modern optics and materials engineering. These lab-grown crystals are essential components in laser systems, optical isolators, fiber optic communication, and magneto-optic sensors, where their optical transparency, thermal stability, and refractive precision make them irreplaceable. Garnet materials are also used as host crystals in solid-state lasers for everything from medical devices to industrial cutting tools. Even in abrasive form, garnet's natural hardness, Mohs 6.5 to 7.5, and lack of cleavage make it ideal for water jet cutting, sandblasting, and precision polishing, especially in aerospace and high-performance manufacturing. Garnet's versatility sets it apart. It performs in delicate photonic systems with the same efficiency in high-pressure industrial environments. Unlike many gems, garnet bridges the gap between the natural world's beauty and modern engineering's demands. It's a stone that doesn't just shine, it works. In that way, garnet earns its place among the most useful and underestimated materials shaping today's high-tech world. Ranked fourth, ruby, the gem that sparked the laser revolution. Ruby is not only a symbol of royalty and passion, it's the gemstone that ignited the age of modern photonics. As a chromium-doped variety of corundum, ruby combines stunning red fluorescence with superior material performance. With a Mohs hardness of 9, exceptional thermal stability, and resistance to chemical corrosion, synthetic ruby became the world's first laser medium in 1960, forever earning its place in technological history. That groundbreaking ruby laser wasn't just a scientific novelty, it laid the foundation for laser applications in medicine, communication, defense, and industry. Today, synthetic rubies are used in solid-state lasers, gyroscopic navigation systems, precision medical instruments, and ultra-durable watch bearings, where accuracy, strength, and low-friction performance are mission-critical. Ruby's optical properties, including strong absorption in green light and emission in deep red, make it ideal for pulsed and continuous laser systems, particularly where stable performance under high energy is required. While natural rubies remain prized for their saturated pigeon's blood hues, ruby's role in engineering and optics sets it apart as a true dual-purpose gem, as elegant as it is effective. Ruby isn't just beautiful, it's a high-performance crystal, bridging the worlds of luxury, legacy, and laser-driven innovation. Ranked third, sapphire, the crystal behind your screen and sensors. Sapphire is a variety of corundum. Sapphire ranks 9 on the Mohs scale, making it nearly as hard as diamond. This exceptional hardness, combined with chemical stability and high thermal resistance, gives sapphire a dual identity. A coveted jewel in fine jewelry, and a high-performance material in cutting-edge technology. In its synthetic form, grown through the Verneuil or Czochralski process, sapphire is used in LED substrates, optical windows, biometric sensors, semiconductor wafers, and infrared systems. Its ability to transmit light across the UV, visible, and infrared spectrums, while resisting scratches and extreme temperatures, makes it a go-to material for everything from military optics to smartphone camera lenses. If you own a high-end smartwatch or flagship phone, there's a good chance sapphire is protecting your screen or lens. Even in luxury, sapphire maintains its allure, especially the rare natural cornflower blue stones from Kashmir, which can fetch over $20,000 per carat. But beyond its brilliance and durability, sapphire symbolizes clarity, wisdom, and resilience. And that's precisely what it delivers. It doesn't just dazzle in crowns or engagement rings. It works silently and powerfully in the background of your daily life and at the forefront of innovation. Sapphire is where elegance meets engineering, a crystal that protects, performs, and persists. Ranked second, quartz, the crystal that keeps the world on time. Quartz may be one of the most common minerals on Earth, but in its pure crystalline form, it's a cornerstone of modern technology. Composed of silicon dioxide, quartz ranks 7th on the Mohs scale, making it both durable and optically stable. But what sets quartz apart isn't just its physical toughness, its piezoelectric property, the ability to convert mechanical pressure into electrical energy and vice versa. This unique trait makes quartz the heartbeat of timekeeping, powering everything from wristwatches to smartphones to satellite navigation systems. The crystal's ability to vibrate at a precise frequency, most commonly 32,768 Hz, allows digital clocks to keep exact time. Beyond horology, quartz is essential in oscillators, radio transmitters, GPS systems, medical imaging devices, and pressure sensors. Its role in technology is silent but omnipresent. At the same time, quartz remains a beloved gem in its many varieties: amethyst, citrine, rose quartz, and classic rock crystal. With a refractive index of around 1.54, it offers a clean brilliance and is often cut into affordable yet elegant gemstones. Quartz bridges two worlds, the raw earth and the digital frontier, in both natural and lab-grown forms. It stabilizes signals, aligns frequencies, and keeps systems in sync. In short, quartz doesn't just sparkle, it resonates, shaping the rhythm of the modern world with every silent pulse. In the first place, diamond, nature's hardest material, meets the future. Diamond is far more than just the symbol of love and luxury. It's a material at the pinnacle of natural engineering. Made entirely of carbon atoms arranged in a perfect tetrahedral lattice, diamond is the hardest natural substance on Earth, scoring a 10 on the Mohs scale and withstanding pressures up to 100 gigapascals. But what truly sets it apart isn't just hardness. It's the combination of properties no other material offers. Diamond has an extraordinarily high thermal conductivity, up to 2,000 watts per meter per Kelvin, 5 times that of copper, making it ideal for dissipating heat in high-performance electronics while simultaneously acting as an electrical insulator, a rare and valuable trait. With a wide band gap, diamond is being explored as the next-generation semiconductor for high-power, high-frequency devices, especially where traditional materials like silicon fall short. Synthetic diamonds grown using CVD or HPHT methods are now used in quantum computing, laser optics, biomedical sensors, and even diamond anvil cells that recreate the pressure of Earth's core. While it still dazzles in engagement rings with its high refractive index of 2.42 and unmatched brilliance, the diamond has become a cornerstone of modern material science. Its ability to perform under extreme conditions, conduct heat without electricity, and survive radiation makes it a leading material in aerospace, defense, medical, and nanoelectronics. Diamond isn't just beautiful, it's indispensable, so it stands at the top of the list of technologically significant gemstones. Gemstones have always captivated human imagination, but their true power lies beneath the surface. These 10 materials prove that beauty and utility are not mutually exclusive. As technology continues to demand more from the materials we use, these gemstones are stepping out of the jewelry box and into the laboratories, satellites, and surgical theaters of the modern world. The next time you see a sparkling stone, remember that it might be holding your data, guiding your flight, or focusing your laser beam. Let us know which resonates with you in the comments, and don't forget to like and subscribe to our channel for more content like this.